Hi everyone. So I'm Guillaume. I will speak about some classification problems and especially about scikit-learn today. So just a bit of background. I'm an open source software engineer as the foundations at INRIA, which is based in Paris, and mainly working on scikit-learns. And I'm also a contributor of imbalance learn, which is something that we will see today. I mean, this is one of the topics that is an angle that I will use today to present some insight on some classifications. So to give a bit of background, in the past, I worked during my PhD. Basically, I work on imbalance classifications. The idea was to find cancer on MRI images, like the one that is here, and usually you have a problem that is called like imbalance problem, because you have many pixels of voxels that are considered like non-cancerous, and some of them are only cancerous. So you have a ratio between those two classes, which are kind of like really different. So in that case, you have like 20 pixels that are non-cancerous for one pixel that is cancerous, and that makes a kind of a challenge, basically, when you want to tackle these problems. So if you have such problem, usually when you want to start to work on that problems, you will start to look at the literatures. So you go to the nice libraries and look at what people are doing. And if you look at these specific problems, you will find articles that say, oh, actually, you have tricks to manage that. And you have some that are like more common than others. And for instance, one of the things that is very popular is like sampling. So for instance, modes is one of these methods. And somehow, because they are as well like doing the PhD, doing code, one thing that you come with is, okay, maybe I can do a tools that everybody can use. So I was using Scikit-learn at that time for my, let's say, predictive pipelines. Then I decided to basically make another libraries which can be compatible with Scikit-learn that allow basically to make those type of resampling there inside those pipelines. And then you can just like fuse those, create a pipeline, put it inside your cross validation, and at the end of the day, you are happy with that. Then because it's good, you start to write articles, you go to conferences, and you start to speak about it. And then, like a couple of years later, because you still, I mean, I have the chance to still work on section and discuss with people on some other trouble, you see that life is not that simple. And if I have to rename basically the talk of today, that would be more the following, which is learning from imbalanced data. I was pretty wrong to do all of this, but I was not the only one. So here, I will just like take the angle of the imbalance problem and to state like have some strong opinion on that, and then I will show basically a use case where I will show usually what we do, what the state of the art is telling you to do, and on the other side show like what are the mistakes that are done on this path and how to solve them, and then I will show as well how in Scikit-learn we are like providing new tools basically to tackle the real problem, the root of the problems. So the first thing is that after 6 years, I just realized that there's no problem with imbalanced data. And the intuition that you can have behind is this intuition, for instance, from this article from one of the contributors of Scikit-learn as well, which is Christian Roetzen, which is you are not creating magical data out of nowhere. So you cannot do like much more than what you have. So like resampling is actually pretty not something. I mean, it's not creating so much information. And the changes that you see is probably coming from something else, and it's what you need to understand. So the typical use case here that I will take a data sets, which is an adult census data sets. So it has a mix of categorical and numerical features. And I resample a bit more to have like a rare imbalance case. So I have almost 40,000 cases that I have people earning below 50K dollars per year, and people that are earning above 50K. Okay, so you have like a ratio, a larger ratio between both. So typically, if you use like the vanilla, let's say, models from Scikit-learn, so here I'm taking two type of model, and there's a reason behind it. So one is a linear model, and the other one is a random forest. So it's because I want to use in one resampling, so that will be the linear model, and in the other one that will be the random forest, because I have another type of forest which is called balanced random forest later. And we can make a direct comparison between those models. So if I run basically a cross validations on those data using the balanced accuracy, so I will come again later on why to use, maybe this is not the paid choices, but let's use what people are using normally, then you will get those type of results. So you will get kind of low score to what you could expect. Okay, so the one is around 0.55, the one around 65, and what you are seeking is to improve that metric. So to do that, you check the state of the art and you say, okay, so I can look at what people do, and then is where the resampling come into. So SMOTs will allow you, for instance, to resample the dataset and oversample basically the dataset before to make your logistic regressions. And on the other side, you will have the balanced random forest. And I will just go to the next slide. And the idea of balanced random forest is that each of the bootstrapped will be as well sampled such that you have balanced bootstrap for each of the tree that you train. Okay. And using those methods, you can like fit those models which are that see basically a bit different data, and at the time of prediction basically you don't do anything. Okay, so you just predict on the real data. And if you do that, then you see a push of performance, and you could call it a day. Okay, it's what you obtain, so you are really happy with that. You are beating the like the state of the art, let's say, and then you should be happy with that. But there's trouble here. So there is two of them. So one is like when we do the resampling, we are actually not checking. Let's say we don't try to optimize anything with it. So is it like the best strategy that we can have? Is it so when we do resample, should we optimize something? And this is really not clear why we should do that. So we could still make a grid search, but then we'll see this is really like not the best strategy either. And then the second thing is that because what we'll see just next, you are actually doing something wrong with the classifier that could be actually a trouble, I mean, a big trouble for you. So what is this params is about calibrations. And it comes to if you try to use basically the probability estimate that are provided by your classifier. And by doing a vanilla, so in those figures, what we have is like what we call a reliability diagram. And meaning if can I trust basically the probability that my classifier is providing to me. And in the case of the vanilla classifiers, who are more or less, when the classifier, let's say, you have 30% of chance that this is this class, actually is not far from the truth, okay? And by doing resampling, the only thing that we do is that we are breaking these calibrations. And when the classifier tells us that you have 30% of chance to be class one, actually this is not the case because the sampling just like makes the classifier usually overconfident because we push him towards telling us there is a concept that happened. And why people are using resampling at the end is because we have this hash threshold that say above 50% will declare you as class one, and below 50% you will be declared at class zero. And the only thing that the resampling is doing is kind of moving this threshold without controlling it, but moving this threshold towards the decision that we want, okay, that optimize basically the metric that we expect. And so in this case, it means that we get the prediction that we want, but we already like broke the probabilities. And in the remaining here, it will be just to show you that you can still fit a good probabilistic classifiers and then tune the threshold that shouldn't be the default at 0.5, and then you'll get the best of the two worlds. So what we are currently working in Scikit-learn, and that will be either in the release of 1.4, that should be in this month, or probably the next release of 1.5, depending if we so we pass the boundary of the release manager, is to have what we call a meta estimators. So these estimators will be in charge of fitting the models, and then afterwards, given the metric, it will tune the threshold that by default is 0.5, but it will move it to where it optimizes the metric that we want. Okay. So if I look at what we have normally in the vanilla case, we would have a cutoff at 0.5, and for instance, here we can see that this is the circles, and we have a low balance accuracy. But then if I compute the balance accuracy for all possible threshold, then I will see that I have a maximum somewhere, and I can pick up this threshold, which is 0.04%, basically, a probability of 0.4%. And above it, I can say that you will be, in that case, so this is like you will earn above 50,000, and below that, it will be you earn under 50,000. So at the end of the day, you don't change your classifier at all. The only thing that you change is your decisions. So it's the ROC curve. If you compute a ROC curve, the curve is exactly the same for the two classifiers. And the only thing that you are doing is moving along that ROC curve. And in terms of, like, if you want to understand in terms of decision, you really are just modifying basically the number that you have inside the coefficient matrix. So in this case, we detect more cases that we have above 50K, but we start to make more false positive, and but we do a bit less false negatives. And in total, basically, this is just a trade-off. So here, this classifier is really intended when you want to go from probability to actually make decisions. So here we just apply the classifiers on our previous programs, where we'll use on one side the vanilla logistic regressions and the vanilla random forest, and just tunes both approach. And then we observe that we are very close to what the sampling is doing. I mean, almost. So for the logistic regression, we are fine. And yeah, for the random forest, we're still a bit below the balanced random forest. And here, one would say, yeah, I mean, it's like 15 minutes that you speak and you say that you should do that, but then at the end, it doesn't work better. So there's something that we missed. And what we missed is basically, we all forgot to grid search our models. And this is something which is super important. And the reason here, and we'll see, is that our random forest is still somehow overfitting. And by changing things and basically finding a model that less overfits, I will show that basically you go back to the balanced random forest. And when you do the fine-tuning, the important things to do, and which is not the default in Scikit-learn, and that we probably are intending to change in the future. So when you do the grid search, you should use what we call a proper scoring rules. So the barrier score or the log loss for classifications. And the reason is because when you go from these proper scoring rules to a thresholded rule, like balance accuracy or accuracy, you are losing informations. And by doing the grid search, you might just like lie to yourselves. So for instance, here on those figures, this is the same models. And I will see here that I have a minimum. So because I have the model that overfit after 1,000 leaves, I cannot see really what happened here. But here I have a minimum around those 100 or 200 leaves. And this, you cannot see it when you use the balance accuracy. Because what happened is that when you go to the threshold method, you have several models that could be equivalent. But then inside those equivalent models, there's probably one which is actually the best one when you use the proper scoring rules. And the thing to understand as well is that the proper scoring rules is just trying to optimize the probability estimations. So one is use the right metric. And the second one here that we can have is like to understand why we didn't have as a good random forest compared to a balanced random forest. And if we look at the figures from the right, we see that we have a kind where we reach a plateau. And actually, this is the effect of the resampling. And the resampling, because we have less data, our forest was the sampling was playing as a regularizations. It was allowing us to not get trees that were overfitting the data. While in the case on the left, because we have like much more data, there's a point that over 1,000 leaves, we were starting to overfit. So we probably have a much better model between, let's say, we have a better model in 100 leaves compared to the model on the right. But then if we were not optimizing the number of leaves, then we end up inside the regime where we overfit. So here, if we tune properly the models, and then we pick up the best maximum number of leaves on the log loss. So this is a result that we have before, and we'll see that if you optimize that, then you will just move the model up. And in that case, you are in the same, like both models are as good, okay? But the big difference here, you are basically accounting for the metric that you optimize. I mean, you are controlling everything, while this is not something that you are doing during the resampling. And then there's cases that the resampling doesn't work, and here you are sure that basically it will just try to optimize what you are looking for. So now this is something as well. I mean, this meta estimator is allowing for something additional, which are like very, very interesting for. I mean, that's like the major feature of that features. Leveraging something that we call metadata routing. So, and I will come like explain with an example what it is. We can actually define business metric, which was not the case in the past. So metadata routing is very useful in that particular case. So let's imagine that you have a credit card fraud examples, and the cost that you have is not anymore a balance accuracy or precision or recall, let's say that you define statistically, but really like dollars or euros. And then what you want is a classifier that maximizes your revenue. So you want to decrease the cost as much as possible or maximize the gain in this case. And usually what your business people are interested about that, not about your balance accuracy. Okay, so here what we'll show is that you can use this tune classifier to optimize the decision threshold using those business metrics that you define yourself. So in this case, we can go around like a credit card fraud examples where you will have different values. But the important part is that the amount that you have here is not a feature part of your data, neither from your target. This is an external thing that you can have, but somehow you want to bring into your models during the fitting, but it's not present in your data or inside the target, or it shouldn't be part of, like, let's say the link between this amount and the Y, potentially. And in this case, this is what we call metadata. So here, how we want to define a metric that uses these informations is we would like to define a business metric that will take Y true and Y pred, which is really what is output, the output of your classifiers. And on the other side, these meta informations, and this business metric here that is defined here is exactly a multiplication between the confusion matrix and the cost matrix that we got. And then we should sum everything, and it's telling us what is the gain that we obtain. And in Scikit-learn 1.4, you will already be able for sure to have those business metrics. So you need to enable the metadata routing. Then you can create a scorer that takes my business metric. And then you just have to mention that there's some new metadata, which will be amount. And then you will it will allow basically in the next stage to say to the scorers, take this information and provide it to the business metric as a parameter. Okay, so it's what happened here. I can call these scorers where I pass my model, the data, and the targets, which are like the free information that we could already do. And this additional information about amount. And this amount here will be dispatched basically to the business metric. Then I'm able to compute scores that take into account this metadata. Then we have this, how can I like play with the cost sensitive learning? So it's to use like the tune threshold classifiers. And the objective metric here is not anymore the balance accuracy, but this business metric. And then at fit time, I can pass these informations amounts which is for the training, this is the Hammond train, and during the evaluations, I can pass the Hammond test. And then I will get basically in dollars or in euros, what is the gain what is the gain of my classifier. So we can as well use this inside the cross-validation. And in that case, what I obtain is exactly these things. Okay, so you get your model, your data, and your targets, you pass the metadata, and you pass the scoring that you want. And in this case, that we can see that the vanilla logistic regression that didn't use the amount during the fitting, didn't try to optimize that, is much worse than what you obtain when you post-tune basically the logistic regression for that specific metric. And in this case, I would say this is super important to use whenever you can a business metric instead of an accuracy or like prediction or recall when it comes to take a decision, because it's usually what you marketing people will want. So as a conclusion here, I have a couple of messages, which is stop resampling to fight class imbalance, because there is no problem of class imbalance. It's just a problem of, let's say, design of classifier that during a long time we just fixed it to 0.5 in Scikit-learn, but not only in Scikit-learn, and everybody was using this type of things. And it comes just to like tune these parameters. Second message is tune the hyperparameters of predictive model. I mean, this is a given. But what is not a given, and because it's not the default, is use proper scoring rules. So unthresholded probabilistic metric like log loss or Breyer score. And then the one that we saw today is at the time that you want to make a decisions, you can tune using a real business metric. And then last message, because this is a free one, just like always cross-validate. Okay, that's super important. Okay, thanks for your time. And that's now if you have any questions, I can answer them.
I would say that was almost perfect timing, right? With 6 minutes left for Q&A. Thank you, Guillaume, for that. There are some questions. When will the PR?
Yeah, so I can read the first one. So when will the PR be accepted? So the PR, it's just, so because we are doing the release of 1.4 that will arrive in December, we might not do the cuts because we need a bit more review. I mean, we are sure that we are going to merge it. So if it's not merged this time, it will be merged in, let's say, for the next release, which will be June. I'm pushing so that it is going in, but Christmas is coming, so it's complicated. But it will be either in 1.4 or either in 1.5. Second question is the new tuned Schroeder classifier model agnostic? And I would say yes. You can pass the models. And it's just that the EJBoost need to implement the metadata routing that we are doing in Scikit-learn, and we might see with them if we can improve that. And then can cost gain matrix be helpful in imbalance cases? This is exactly what I did like inside the last example, basically. So yeah, this is. So I don't know if there's any other questions.
I was going to say there might be some more in chat. You are getting a nice little shout out. Currently the best presentation, in my opinion. Love that. But it looks like Anton's might have a quick question as well that we hit on before heading out.
Wait, so I'm looking at the chat now. What about the cases with extreme? So the extreme case is exactly the same. I mean, it's just that usually, even you have very large cases, it's just coming by when you come to the decision, it's just a matter of how you are moving those things. At the end is what machine learning is trying to do is to optimize a proper scoring rules and a probabilistic classifier. So until that you optimize that, then you are fine, and then the decision come afterwards. And it's like that's why you need to optimize with a grid search the log loss and the Breyer score. That's the most important thing. And then it's just tuning. If you try to go in between, then you will not get through the right probability, and you will not have something that you expect. The class weights, so I see, what about the class weights? Do they mess up the calibration? It's exactly a resampling under the hood. So it's messing up the calibration as well. Okay. When to use calibrations? So you shouldn't do, let's say you should look at the classifier, make your reliability plots. If you see that your classifier is not well calibrated, then you will need to calibrate it. And this is kind of important, let's say, when you really want to use the probabilities output of the classifier. I think I did all of them. And
yeah, there's a few
ones.
more of that. Yeah, in the Q&A section.
Yes. So the question about that you can get a positive number from the cost matrix even because you have large numbers. At the end of the day, your metric is summarizing this cost matrix, adding everything together, and you try to maximize it or minimize it. And at the end of the day, it's like you try to maximize the gain. So it doesn't matter what you try. I mean, somehow is that this is linked to what you try to optimize. So I don't see any problem with that. But I would be happy, like if you have counter examples, I mean, I would be happy to see that. So the Matthew core coef, I mean, to be more efficient, I'm not really sure. So the thing that the Matthew core coef is better than balance accuracy and all of this in the way that it's consuming the full confusion matrix statistics. But at the end, optimizing this metric doesn't mean that you optimize, this is not a proper scoring rule, so you don't get the best probability classifier. And that's what is like problematic here. And by being more efficient, I would say, argue that I want to see it, and I want to see with cross-validation to not be to be sure that we are not inside error bars of things. Okay, so somehow, I mean, I would say, okay, but I need to see why. I mean, if there's like, what are the experiments behind that? In a few seconds, why not resampling for class imbalance? I mean, the only place that you can still want to imbalance is maybe to speed up your learning. So you might want to resamples, fit the classifiers, and then you need to recalibrate your classifier. But because you train on less data, and maybe it's good enough, then you can basically still use a resampling for that specific use case. But in general, this is not great if you try to get a calibrated classifier. So if you resample, you will need to recalibrate your classifier. And the second thing that with this resampling, you are not controlling for everything. So you are not controlling for the best decisions that you can get at the end.